Yeah, so trying to justify this construction of a random graph, I realized like, okay, it has some meaning, but maybe it's not like uh, super good, right? So one thing you can do to interpret what we mean by the union of the two data frames is simply do this D3 visualization on by superimposing the two, right? So you can take this and superimpose it with this, because the total number of the nodes are fixed. Uh, so but if you just put them all in a bag and draw edges at random, it's something, but it's not necessarily emulating some kind of say, each node is IP address and it's sniffing around behavior, right? Because if it's sniffing around, then there may be some kind of time lag, right? So it may be that um, some bot tries to, is our star node 0, and then every few seconds it just sniffs to another, right? So which means there may be patterns in the times of occurrences of these edges coming out of 0, right? And in fact, a lot of these DNS based algorithms, they actually look at the time from a particular IP, going out to an external IP, some kind of command and control center. And some algorithms actually look at the periodicity of these sort of communication with the control center, right? So, but if it's a local infection, that means, nodes within the internal network are being scanned, then again, it's going to depend on how clever the bot is or the scanning thing is. It could be silly and just start scanning immediately, like boom, 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 boom. If it does that, then of course the random graph model has to be different, right? And we need to, a more complicated simulation scheme, right? Do you guys know hidden Markov models?
Yeah.
Okay, so for example, you can have a hidden Markov model and be in the state of star world, and and then with some probability switch to this other state, right? So, I don't want to complicate it too much, because what we will do in the end is we'll take stuff. So for example, we could look at the total number of out edges of in a watermarked window of a structured stream of these edges coming at us, right? So then I can count how many, what is the degree of each node in some thing, and I can raise alerts if the number of degrees is more than some expected threshold, right? Say that could be a very natural alert for a scan attack, for example. Mm-hmm. So what we will do now is learn a little bit about sketching, and then we can use this rather popular scheme called T-Digest that is very good for lots of problems detecting anomalies. Okay, I mentioned briefly yesterday the basic idea of even Fisher, who noticed this fundamental computational difference between computing the mean of a stream of data, variance-covariance matrix of a stream, versus other things like medians and quantiles. Right? In the first case, we can set up what are called recursively computable structures, data structures. So with a very small memory footprint, we can keep the running mean updated. But keeping the running median updated exactly is non-trivial, because you need basically a sort of everything up to now. So then what people started doing is entering into this world of probabilistic data structures that give you approximations of quantiles rather than exact quantiles. Okay. If you want a more mathematical background for streaming and sketching, I strongly recommend Chapter 7 of this recommended reading book, Foundations of Data Science. It's fairly mathematical, but it's really good. Kind of get you really quickly into Chapter 6. Yeah. Okay, so So, but now let's look at these blogs to get a faster view, and I want to watch this this video about 8 minutes or so, which is quite good, from the guy who invented T-Digest. So this is the blog. Okay, so this is probabilistic data structures. So as I said, the real problem is we want to use less memory in less random access memory and have constant query time. That means if I ask, what's the 99th percentile now? It should answer right away, constant time. And we want it to be parallelizable and so on. So here are some examples of well-known algorithms you should really have under your belt. Some of these are actually implemented as featureizers already in ML pipelines, like and I think Mariama's project will involve minhash or some variant of it. So these are the use cases. So hyperlog log is a approximate counting algorithm, counts the number of distinct elements in a stream. Bloom filter is a set membership thing, and minhash is a similarity operation. T-Digest is what we're going to get into because this will give us streaming quantiles. Why are we after quantiles? Because we want to, raise alerts based on some natural notion of a score. So score is usually some kind of number, and the bigger the score, the more anomalous the phenomenon is. This is usually how you would encode the score. So then if we have lots of scores streaming at us, like say, I don't know, 100,000 every minute or whatever, and they've been streaming at us for a long time, for the last several months or years, then we want to be able to answer questions like, what is the current 99.99 quantile of this streaming score, okay? And if we can answer that question, then we can ask, let me flag all the events whose score is bigger than this threshold, for example, right? So, that's kind of a general framework for a lot of problems in so-called anomaly detection. You don't know what's going on and you want to investigate, or other problems called predictive maintenance, which is a big problem in all industries. So you want to, essentially you have streaming data from sensors of washing machines and chainsaws and bulldozers, whatever, right now, and these are coming at you, and the simple things people do, it's fairly useful, is simply report the, the 75th quartiles, quartiles, 25, 75 quantiles, and maybe then 0.99 quantile. And you can just color code them by different alert levels. And so especially if a sensor is just, too hot, something maybe is going on, or so a lot of the things are doable now in a univariate setting, and T-Digests are generally univariate. So if you have a metric stream of vectors, say 10 different measurements from sensors, then usually you will do the T-Digest for each one of these coordinates. As far as I know, being able to do quantiles or generalizations of quantiles for bivariate and multivariate distributions is still an open problem, as far as I know. So, currently some of my big data research is focused on this, and our own Tilo thinks he has a solution, so which is good. Okay, so I don't want to go too much into it. This is a great blog. I just found it recently. So let's just jump directly into let's see, into the T-Digest one. I think that's this. So here's the man. Let's listen to him. Give me a sec. Whiteboard walkthrough. That was pretty cool.
I'm here at Scalable. It's winding down for the day, but I'd like to talk about a little bit of data mining. In particular, about a technique called the T-digest. T-digest is a really cool box that you can add to an anomaly detector so that you can set the number of alarms as a percentage of the total samples that you get. What it does is it actually estimates percentiles very, very accurately, especially high or low percentiles. And by estimating these accurately for you, you can set a threshold automatically by defining what percentile of the samples you'd like to have alarms. Before we go, who's the hat? So let's have a talk here. We're going to talk about this algorithm called T-digest. It's named kind of in analogy to another algorithm, an earlier one called Q-digest. And almost all of the previous algorithms for computing quantiles did one particular thing. They computed approximate quantiles, and the quantile, the value that you got as an estimate for quantile or percentile, was accurate in terms of quantile space to within a constant error. That means you might get a median plus or minus 0.1%, or the 90th percentile plus or minus 1%. Now that makes very little sense to have the 99.999th percentile plus or minus 0.1%, because that's not really the 5 nines anymore. So the interesting thing about T-digest is that it is a very, very simple algorithm, and it allows controllable accuracy, especially at the tails. Now the way it does, we take some value x that has an unknown distribution, and we're going to take samples from x, 1 through n of those samples. And what we're going to do is we're going to compute this high nines or very high zeros percentile, and we're going to do it controlled accuracy. And typically we want part per million sort of accuracies for these very high percentiles. That's part per million in terms of percentiles, of course. If it's a very skewed distribution, the actual accuracy in the original measurements might be a very large error, which might result in a very small percentile error. So what we do is T-digest is just clustering. The basic algorithm is almost identical to k-means clustering, except that there's a size limit. And the clusters in T-digest can be large when Q is near 0.5, but there's a very strict limit applied to centroids that are near 0 or near 1 in this quantile space. And in fact, the limit that we use nowadays in the T-digest is the square root of Q times 1 minus Q. That goes to 0 at the ends, and so on. The square root comes about because the error in the estimation is proportional to the square of the fraction of the samples that is in a particular bucket, a particular centroid. And that's because the linear interpolation errors are second order in this size. And that means by making the square root of this, then our error is proportional, our relative error is proportional to Q times 1 minus Q. That means it's constant relative error at the boundaries, either at 0 or at 1. You get constant relative error there by having this variable limit. Now, most algorithms don't subject themselves to this limitation on size very easily. With T-digest, it's just clustering. The algorithm, essentially, without some special cases, is to find the nearest clusters. Now, there might be several at the same distance. If one of them is small enough, meaning less than the size limit, you can just add x to it. That means increase the weight that it has and adjust the mean. These are standard sorts of things. If the nearest cluster is too big according to this limit, then we make x be a new cluster. That's the algorithm. Now, there's special cases where you might have data in order or nearly in order, and the number of clusters would grow because x would always be nearest the biggest thing, which is always at the extreme. So it always has a 0 acceptable size. Therefore, we keep adding new things. And in that case, what we do is we take all the samples that we've collected, randomize the order, and just rerun on those samples. And that will give us the bounds that we like. That's a special case, but it's not a very interesting or difficult special case. And so the exciting thing is that even though we get part per million accuracy of these high or low quantiles, the size of the t-digest for the square root limit is known to be pi over 2 delta. Delta is a quality factor, and 1 over delta is kind of the size that we're aiming at. So very common setting is 1 over delta equal to 200. And so pi over 2 is 1.57 or so. 200 times that would be about 300 samples. That gives us part per million accuracy at the tails and very good accuracy at the median. If we wanted a little bit less accuracy, we might pick 50. And that would mean that the number of samples that are kept, the number of centroids, would converge to about 78. It's a very small number. No matter how many data points we have, millions, tens of millions, billions even, we could capture that in just a few hundred centroids. If we use a constant size limit across there, which would be more like other algorithms in this space, then we get to a size limit of just 1 over delta. So we would come up with 50 samples if 1 over delta is 50. Now, if we get rid of the square root, which gives us slightly better accuracy, and it might, in particular cases of very, very high skew, give us better accuracies, then the size of the Q-digest grows without bound, but it grows very slowly. With 100 million data points, we typically have a few hundred centroids required. So it still grows without bounds. That's theoretically not so nice, but practically it may not be a big problem. This is really, really useful if you want to have quantiles of a huge number of statistical buckets. How is the viewing time in this location, in that location, in this demographic, in this demographic, in that location. Because these things are bounded to such small sizes, we can keep billions of them, literally billions, and still get very accurate quantiles. And that's exciting because quantiles are a very important sort of aggregate that we might want. We can even combine these t-digests that are computed on separate pieces of data and get a combined t-digest which has the same properties with regard to size and accuracy. So that's the t-digest. It's really simple, even with the Greek letters. And I don't even have any Greek letters. See?
Yes,
there you go, except pi. That hardly counts. Thank you very much.
All right. I thought you should hear from the man. So there was a paper. It's a pretty heavy paper. You can read. So there are some implementations or uses of t-digest I feel are not correct out in the real world, but that's okay. That's a different problem. But if you're using it for quantiles, it's fine. Okay. So this is actually now there are many libraries. Of course, Ted Dunning has his own library. What I wanted to let's see, it's here maybe. So what we want to do is import this library. So you can just copy this, ISAN, sketches, part 211, blah, blah, blah. And this is the Maven coordinate. So you can just copy paste into import library. Right. So do this, and because we will need this. We're not going to write all of t-digest here. So you know how to do this, right? Import. Create library and Maven coordinates, and just paste that here. It should just work. I'm not going to do it because I already imported. So or you can just do a search and hit it. Okay, so Eric Erlandsson has been quite good. I've been emailing him trying to move this into structured streaming. So he himself was not familiar too much with structured streaming, and I think we have it cracked, especially with help from data scientists at Compion. So we will come back to this in the full-blown streaming context next week, hopefully. So here is the find the I'm trying to find a good README file. All right, let's just click here. So is everyone imported successfully? Okay. So so now we have a whole bunch of imports from this project. So this is just our little friend, mixture of two normals, centered at 1 and 10, standard deviation 1, 99 and 1% mixture. So okay, so now I'm just making 1,000 of these samples, and okay, this is what we have. And when we display it, no surprises, we get our little humps, right? And these things we are saying is the anomaly. Okay, this is a baby problem. I mean, if you didn't have this, the t-digest, so everything we'll do now will still work. It'll simply detect the outliers on the positive side, 0, right? If I didn't have this hump, right, the 99th quantile will be here, so it'll just detect. So it's called outlier detection in classical statistics. It could be anomalous. That's a different problem. Okay, so now this delta is that so 1 over delta roughly gives you the number of clusters, right? These weighted centroids representing your stream. So I'm just taking the 0.2, and there's this extra option to use this max discrete 25. So if there are fewer observations or they're coarse, then it'll use a discrete version of t-digest up to 25 bins, and then if it's more than that, it's really a continuous stream, then it will switch to this version. So you can do that if you want. So now what we've defined is this t-digest user-defined aggregate function thing. Right? So I'm sort of packing it a little bit at a time. So remember, data is just our raw data. Data frame of doubles. I can now call the aggregate method for a data frame where I'm passing it the user-defined function that I've just created, right? And that's acting on the value column of my data. So this is basically the simplest example in this README file of Eric's repo, and he has. I'll find out the right place to get this, but he has a much more elaborate version. In that version, he has like multiple. He has multiple. Sorry, I can't find the repo right now. He has examples where you have MLlib vectors and all sorts of multivariate streams, and you can apply this column specifically, And in fact, he uses t-digest in much more sophisticated ways for other ML problems, even including randomizations and random forests and all sorts of things. Okay, so that's it. So we've aggregated now, and then now if we take this ag thing apart, we take the first and then get as t-digest SQL. So this is a an SQL wrapper for t-digest, and then ask what it is. So this is the basic object we're working with. So you can see what it is. It's a t-digest object with I think this is the delta value, the bins, and then it has this map with the centroids and weights and so on. So
I have a question. Yeah. So the aggregate will take every row and apply the UDAF on the value column.
Yeah.
Right. And then the UDAF is the whole algorithm, clustering algorithm.
Yeah. So UDAF is basically our interface into, because all the code is pure Scala, so you can pass user-defined aggregate functions into Spark SQL. So the catalyst optimization, all that will happen now. So you can just think of this as adding, right? In built-in user-defined aggregate function is sum.
Yeah, but the UDAF is a mutable thing. Oh,
it's just aggregating all the.
It's folding all the.
Yes, exactly. Yeah.
Okay.
Yeah, it's aggregating it and just giving you a t-digest. So it's
okay.
Simplest thing right now, right?
Okay.
We'll do crazy things soon. We'll have like data frames of t-digest.
Okay.
So the first thing you want to do with the t-digest object is evaluate the CDF. This is it's an empirical CDF of the approximation. So you can ask what's the CDF at 0, right? So this is actually literally, what is the cumulative distribution function under this approximation at 0, okay? So it's 0.16, so let's be a bit live right now, and I have no idea, I hope this is not going to crash. This is like very, very raw code. So what I've now done is just turn this into everything is coming from my normal, right, at 1. So I have no little bump thingy majig. So this bump should disappear now. Yeah, good. So now if you now imagine this as a density to normalization and integrate that, you'll get this CDF, right? It'll be like this S-shaped thingy. So now, so if you look at what's the cumulative distribution function at 1, we should get half, right? Close to half. Let's see what happens. I'm going to just redo this, aggregate it. Do that. So now let's just see what CDF of 0 is. Did I do something? Double delta data. Yeah, change data, right? Yeah. So CDF.
But you get 1.
Am I doing something?
Get 1.
Yeah, 1.
Now it should be
0. 0.5, yeah, okay, good, right. Yeah, but the number I thought didn't change when I left it at 0. Anyway, this makes sense, right? So this is our CDF of the t-digest approximation of the empirical CDF. Okay, so let's just play with this. It's 0.99. So this is now, if I just apply this, so people studying various academic disciplines will fight, and they'll say this is outlier detection. That's the standard statistical name for this, and that's correct, right? But and then yeah. So let me just go back and change this. Otherwise, I might get into some academic war about what is anomaly and what's outlier and all this. So let's just go. So now I am just saying that tiny bump on the right is my anomaly by definition. Okay, so aggregate it, and I don't really. Okay, so now, yeah, I mean, it's just almost 0.5 still because
It was 99%.
Yeah. it's very little. So now this is the inverse. So now it's different, right? It's 9. So these are, because the other thing is centered at 10. So it's just rigged up, right? So if I increase this, All right, so let's leave it like that. That's my cutoff. And so let's flag those points that cross the threshold. What am I doing? Just taking the data, adding another column called anomalous, and putting a Boolean. If the value is more than cutoff, just flag it. So if I show, then I basically get value that's anomalous or not, right?
So these are our values. These are our values.
Well, yeah, so if you want. Yeah, I'm now boldly saying it's an anomaly because I put the little bump, right? So exactly. But if I didn't have the bump, then I think people call this outlier. But remember, like, this is data science, so everything depends on what problem you're actually solving and what word you use and what language is irrelevant, right? As long as the washing machine doesn't break down, that's the problem. So anyway, I'm just sort of showing you this. So this is kind of what's really coming at us in our simulation. So every time there's this little thing in the far right, there's a little anomaly flag raised, right? It's a baby example. Okay, so that's sort of T-digest in a big hurry. So what we really want to do is streaming T-digest. This is almost example 1. So now let's say we have this sort of batch setting, right? So this is so this is one way to, I think this is what I'm trying to do here. So I have my files, which is just the simulation, it's very Gaussian. So now what I'm going to do is create a streaming version of this, okay? So I have my read stream, and my schema is my timed score. And so anyway, if I display it, I'll see the time and the score. Right, this is just the dataset version. It's just recall from yesterday. And if I display this, I'll get a time and a score, but datasets. Now, I will do batch processing to determine the cutoff. This is a standard mode of learning, okay? So what I'm going to do is just run my T-digest on some historical data and just find out what my my threshold is. So this is just static processing, right? So now I literally doing what we did before, right? I am finding my threshold up to some approximation. So my cutoff 99 is simply all of this put together, static lines, data sets, aggregated with this user-defined function, T-digest, CDF inverse, everything we learned in one block now, right? So this is my magical 8.511 is the global cutoff of all this historical data I have. So now let's say real data is coming at us in a stream, and I want to apply this cutoff. So
before we continue, so when I display the stream, I just get null values. So I have the files from yesterday.
Yeah.
They're still there.
Yeah.
But when I just run the display streamline df.
Ooh, right. Okay, that's a good point. Yes. So I think what we need to do is I have some slightly. Let's just run this. Okay. Yeah, I think it's slightly different.
So should I just rerun the whole thing?
Yeah, just rerun it. So yeah. So I'm writing now 20 files, cleaning up everything. I'm sorry, yeah, I forgot, like, there are slight subtle differences in some timestamp. I don't know. Let's just,
Wait, so
this should work.
the one yesterday was called streaming file normal mixture, right? But the sketch is called streaming files.
Yeah.
But I guess I had both.
Yeah. Yeah. So I haven't really optimized it for, I hope you have enough space in your community edition. Yeah. I'm kind of not optimized because I'm not done. I'll tell you in the end why I'm not done, because I want this to be a live streaming update. So it'll sort of stabilize next week. But,
so which one should I be running to generate the correct data files?
I think the one I just ran.
Which one?
040A. I'm pretty sure. Right, so.
Okay.
Yeah. So you see now you can. That was a good finding. So so I have learned this this cutoff, right? So now I have this new streaming data coming at me, and I hope this will just work. Okay, good. So, you know, I'm the pretend playing, right? I sort of generated some data, I pretend that's my historical data, I learned the cutoff. Now with that learned cutoff, which is here, I'm just filtering for anomalies in my new stream that's just running, right? This is not a bad idea for a lot of use cases. In fact, this is all you may be able to do for a lot of problems, until quite recently even. But the latest fad or whatever, which is actually, I like it, is streaming machine learning. So the problem with this approach is that in some problems, in some contexts, this may be not good enough. Right? Because maybe the attack types are changing too quickly, or I have no idea, customer behavior, you know, slightly different in the last day, you know, because you have millions of events pouring at you. So what you would ideally want to do is improve on this pattern, right? Where you learn something in a batch mode and then apply that learned model in the new stream. Maybe what you want to do is constantly update the model itself live, right? Mm-hmm. So, and we're not doing that even for T-Digest right now, right? So, and the same idea works for streaming machine learning problems. So let's see. What was I watching last night? So it took me a while. I sort of watched a lot of stuff, and these are my two favorite picks. The blog is it's from one of those anthologies, the 7 blog posts from yesterday. This one is the thing we really need to understand. What we want to do is flat map groups with state. So this is essentially something that will allow us to do stateful processing of arbitrary, so arbitrary stateful processing. This means like we have, you know, maybe some big watermarked time interval of stuff that's coming at us, and we want to do, you know, we want to maintain a state and update that state based on all the stuff, and the examples you saw even yesterday, like doing word counts on animals, is a baby example of this, where the state you're updating is just the sum, so it was built in. And now we want to do something much more complicated, like a T-Digest, or more general. So if you watch this video from last year, which I recommend, wait, this one I think. There are so it's Ram and this other guy. They're talking about perceptrons, and then streaming. What was it? I think it's a streaming machine learning algorithm. I don't know if it's streaming naive. Oh, it's streaming logistic regression. So that's very close to what people want to do. And then there is I'll fill this up with more blogs, and we will kind of revisit them once we get more into deep learning. We will figure out a deep learned model, say from Google, we download, and then we can just do this batch learned serving of the predictions on streams. But in this case, I'll try to figure out streaming t-digest. And in the last 4 minutes, so this is kind of where so let's see. Yeah, so this is sort of work in progress. So these two pure math guys who used to be in our department, Håkon and Benny, they're data scientists right now, and we're sort of they have this first rollout of flat map groups with state for those arbitrary state updates, and there's a sort of working version now that we're still trying to look at various use cases. So currently, we can have a streaming t-digest that's running on the current batch that's coming at you. And because, remember, the t-digest is a monad, so you can take a t-digest and add another t-digest to it, and do produce another t-digest. So, so we're sort of in this particular append mode. We can actually have the thresholds updated for each batch, right? So this is probably an interesting use case. If I have a large enough watermark, then I can say, in the last 6 hours, give me the high threshold events, right? Flag them. And that code is already here, but we're trying to make this a bit more general because I'm still trying to really learn this as well. So currently, when we initialize the t-digest, if there is no running, state for t-digest, we initialize it from empty. This is like when you're trying to sum, you always start with 0 and add things to 0, right? This is the empty thing. But we are trying to generalize it so that instead of just starting with an empty thing, you can look at a global t-digest up to now and initialize with that. So that way you will have a historical threshold as well. So anyway, all of this is still sort of high-level abstractions. But I think we worked out that there are only 3 real possibilities for arbitrary stateful streaming with 3 t-digests. One, update this this window, and ones that well, anyway, I'll shut up now. I'll talk more about this next week. So I hope you guys play with this random graph example. And who hasn't presented in a while? You've never presented stuff. So what, you want to do a little thing?
Well, what do you want it to?
Well, just create see if you can create a file stream of edges from this simple mixture of, this bag of edges model, right? We just almost cooked it up. I'll upload it. And then maybe just sample edges at random from that union edges and write to a file, and then create another notebook. Now you're trying to, maybe try to make the statistic of interest to be the degrees in some watermark window. So you have timestamps, and then you look at a window, and then you're keeping track of the number of degrees, maybe, and I don't know. I mean, try to, yeah. So the idea is that if you're scanning at some large enough window, we want to detect nodes that are communicating with too many other nodes. That's yeah, and then in you guys too, because that's your sort of basic primitive. So is this still useful? Okay, I don't know, because so there was basically this book by T. Dunning. It's a free book. So in fact, that's the motivation for T Digest. I'm not kind of making it up. Yeah, it's this book. It's available for free. You can download it. It's an excellent book. It has quite a lot of chapters, and a lot of it is focused on this final thing you want as T Digest. So, for example, they have time series models, and in the time series models, they have a reconstruction error, so what the model predicts and what the actual data is, and then they take the reconstruction error, right, into a score, and they T-digest that to detect anomalies, for example. It's one chapter, there's lots of chapters. There's deep learning models there, and if you want to go all out, you can get into autoencoders and do these reconstruction errors. And so I think it's one of the important tools for sketching, getting quantiles. Anyway. Well, you're still coming, It's good.